Hello, Ryan.
Hello, how are you doing?
I'm doing great. How are you doing?
I'm doing pretty well. This has been a really fantastic day so far.
It's quite something, and we're only two-thirds of the way through.
We'll keep it rolling.
We're working our way west. We're almost to the Pacific coast. Two more, three more before we get to the Pacific. So over the mountains.
And over here,
Yeah.
we're snowing.
Oh man. Well, I'm glad I'm not there. So Ryan Lambert of Rustboost Labs is going to talk to us about routing the interesting things, not just roads, with OpenStreetMap. That sounds like a great topic. Take it away, Ryan.
Great, thank you. Yeah, and it's been great to hear the other post-GIS, the other OpenStreetMap talks today, the routing, seeing how fast we can load the data is always fun. I haven't focused on loading planets for a long time, so it's interesting to see how the timings have really continued to drop. My favorite data source to work with spatial data is OpenStreetMap data. And so today we're going to be talking about that with some routing. This is not a live demo. There's way too much to cover for us to get through in this amount of time. So the link at the bottom of this page has all of the resources for today. There are a couple SQL files that you can download, about 400 lines of heavily commented spatial SQL that we'll be talking about. And all of the links that I use in my talk today are also available there. So it's hard to get hyperlinks from a screen share. So we're going to first talk about, where I find interesting things, what I call interesting to route. And we're going to use these as an example as how we can work through some common challenges with routing to get a successful routing project. So the first step is, well, what is interesting to you to route? Because I'm here talking today, I get to choose what's interesting to route. A couple things that I really like working with are the water layers and non-standard people paths. So we talk a lot about, driving on roads with cars. And so we're going to look at some options where that isn't the mode of transport. So these are the broad topics that we'll be looking at. Some interesting things you can do when you're routing in the waterway layers is if you have a contamination or a spill, you can look at downstream effects when it might be able to be cleaned. You can look at floodplains, and even navigation options are available. And people paths, I always like talking about scenic routes because everyone's definition of scenic route is extremely different depending on what you like to do, what you call scenic, and what your day-to-day is. Because some of what we call scenic, here in Colorado might be not necessarily be everything, someone else is considering scenic from a different region. But indoor pedestrian areas is another area of routing that I find really fascinating. And this is a fairly interesting space with some new developments happening all the time with indoor related routing abilities. So when I work with OpenStreetMap data anymore, I pretty much only use the PGOSM Flex Docker image. So this is a Docker container that wraps around all of the dependencies of OSM to PGSQL plus Postgres and PostGIS in order to do the processing. And it really makes it so you don't have to think about what you're doing, which command line options you're running. You tell it what subregion you want to load, how much RAM you want to give the whole process, and it works out the rest and just kind of does all the magic and gives you some high quality OpenStreetMap data to work with. So some challenges with routing. There are a number of challenges with routing, and we're only going to look at a few of them today. There are plenty of nuances and realities with routing and the world that we're trying to route through that make it really tricky to do accurately and completely and for every scenario. The challenges we'll be looking at today, polygons, working with layers and levels as you traverse over or under things, and then various access controls that control the flow of who can go where and how and when. So these are some of the most common challenges that I encounter when I'm working on routing problems. Polygons are a huge challenge with routing because, as has been discussed earlier today, PG routing doesn't deal with polygons. It honestly doesn't even deal with lines, but it has some helper tools that allow us to create these edges and nodes to build that routable network from those line string inputs. When you have polygon inputs, PG routing has no clue what to do with it. That is a pretty big problem when we're working with waterway and pedestrian routes both. So this animation shows the effect that taking polygons out of a water network has. As you can imagine, if you take out these very large polygons that most of the water lines run into or out of, you really get a pretty trashy network of all sorts of orphaned segments that can't be routed to from other areas. So when you don't have the information from these polygons, the routable network of just the lines is very diminished in value. So the link at the bottom of this page here, that blog takes us through the full steps to how to route through polygons with lines. The summary of it here is we start with the medial axis function. This ST approximate medial axis function creates a network of lines within polygons, with the caveat that the lines that it creates do not intersect with the containing polygons. Because of that little gap that is left, we have to create a line to bridge that gap. So we detect where the lines intersect with those polygons, the waterways coming in and the waterways going out, and then we can create a line that bridges that gap from the medial axis out to the outer naturally existing line data. Once we have those three different components, we can glue them all together and then build our routable network from there. And so the post linked here does explain all those details in depth, and it also sets the stage for the rest of the examples we're going to look through. And so the end result of using this medial axis function and bridging the gap of the lines is we have this route that it looks a little awkward, but it's at least routable, which without this trick, we don't have an option to do routing. So it might not be necessarily the perfect line, but it's better than no line. And this allows us to go from the west side to the east side down slope and follow the flow of water. So when it comes to polygon data, we do have a solution available that we can work with and traverse through these polygons with a routable network. Moving along, OpenStreetMap has something in common with ogres and onions. There are layers, and these layers add complexity. When we talk about layers in OpenStreetMap, we have to make sure that we that we're dealing with both types of keys. Layers deals with elements in the outside world. So roads and rivers and culverts and bridges, all of those use the layer tag. When we're working with indoor data, such as inside of a building or a parking garage, all of a sudden it switches to this levels key. And so we have layers and levels in OpenStreetMap. They essentially mean the same basic thing. They're just in a different region. So you need to be aware of the coding and the terminology for the data that you're working with. Another challenge when we're working with layer data, and this is pretty true with most things in OpenStreetMap, it's messy. It's an open project. It's open standards. There's a lot of flexibility and nuance, especially related to localization and how things are built locally and talked about locally, because it really is built with data that reflects the environment of the area. And the first couple examples I gave up here are kind of the ideal layers that we'd like to work with. We'd like to work with 1, 2, 3, 4, 5. We don't get that all the time. Sometimes in buildings, you have areas that extend up multiple floors. And so you get either a 2:3. I really like the example of the -2 - -1, dealing with negatives and dashes interspersed. So it is messy. You have to deal with it. There's half layers. And then, of course, it's not even all required to be numeric. You could have the letter C be a level. So just part of what we have to work with. So when we're working with layer data and building a routable network, We start by creating the routable network, the noded network, using the PGR node network function. The problem for this particular use case is we get false intersections. It will create paths that can't actually happen in the real world. And so an example of that, on the left, we have the OSM representation of two different waterways. And we can see the dashed line going from left to right, indicating that that's an underground layer. This is a small waterway layer that's going underneath a canal that is on the surface. There is not an intersection there, but when we run PGR node networks, as the right-hand image shows, there ends up with a false intersection here in this middle spot, where if you try to route through this network, if you finish building the topology and routing the network, it'll allow traversal from one line to the other, even though in the physical world, that is not a reality for that. So we have this problem of false intersections. So the way we handle that is we run the node network function. We know that we're going to get those false intersections. We have the tools in our hands to find those and fix those. So we start by identifying false networks where there's an intersection in the middle of line strings that from the source OpenStreetMap data, there was not originally an intersection. Once we have identified those false intersections and their component pieces, we can glue them back together with a little bit of spatial SQL. So the code related to this cleanup is in the SQL file, the -- fix levels that you can download. And we'll look at just a couple snippets from that code. So the first part is looking at where the lines overlap, but they didn't actually intersect. And so here we're doing an interesting thing where we actually use the intersects function twice. This first time is finding where the source line strings intersect on an XY plane. So that's just the standard intersection. And then we take a look at the components of those lines. We use the stPoints function to pop out the points, and we find where those points between those two line strings did not intersect. And then, of course, we're using the inequality filter on the layer here to find where those are different layers. So here we're finding the line intersects. There was not originally a point that intersected there, and the layers are different. So this allows us to find those pieces. Once we have found those pieces, we can glue them back together. So the query here that I've extracted, we're pulling from the fix these temporary table that I created there. And then there's an array of IDs that need to be glued back together. So the step before this was where we were finding those intersections, false intersections, and we saved the component pieces as an array of IDs. Here we're grabbing those IDs, pulling those pieces back together using the stCollect function. And then we use the stLineMerge function to avoid errors later on in PG routing. PG routing does not like the multi-line string or multi-geometry type. It really wants the line string input. So this allows us to get the geometry and the base type that PG routing expects. And yes, Thaler, there's looking for tunnel or no tunnel key is also another option. And really with OpenStreetMap data, you need to be looking at all of the different keys and varieties. And it's going to vary from region to region. Some places use keys that other regions don't, but you do need to be very mindful of all of the different layer related tags that OpenStreet has. There's also a bridge tag as well as the tunnel tag. So again, that's just reinforcing the point that it is complicated. But the good news is when it comes to dealing with levels, we have the skills through and the tools through our spatial SQL, through joins and through all the PostGIS functions that allow us to fix the problems. First we have to find them, but once we find them, we can fix them. So that brings us to one of my favorite routing scenarios is indoor pedestrian paths. This I think is just one of those really interesting spaces that is fun to solve these problems. And so the route that I'm looking at here, this is the created route. And the little fun piece of trivia about this route, the input data that I used to create this particular route did not include a single line string. It was built entirely from polygon and point inputs. There are the polygons that define the corridors and the rooms, and the points give us the where the doors to the rooms are. But the actual line data that is involved with this in this particular building is I think there's a few walls or something that that is on one of the floors, but really there's no routable data in the line string data from OpenStreetMap for this particular building. But with the tools that we've talked about previously, with the creating axis in the middle of polygons, and we have the ability to work through this. A quick aside on indoor mapping. Indoor mapping, if you're used to OpenStreetMap or not, it's really worth checking out the wiki page for the indoor mapping stuff. There is a lot of nuance with indoor mapping. It's challenging and it's evolving fairly quickly. So just be aware of the tagging schemes used indoors. Another really quick plug, this indoorequal.org page, this app is relatively new, but it's a way of looking in the browser at OpenStreet indoor map data. So this is that same building, third floor. And on the right-hand side, we have toggles. So we could go down to second floor, or we could go up to fourth floor, fifth floor, and see how the building changes as you go around. So there's some really neat things happening in this overall space as a project. So to create that map for that indoor route, the first step I had to do was cut out overlapping areas. The problem was the corridor that Met Route walks through was one big polygon, and the rooms are inside of it. If we just tried to leave that as is, the routing would think it could go all the way through that whole corridor. So we had to cut out the rooms from the containing corridor first. And then here I'm using the straight skeleton function instead of the medial axis. So it does the same basic type of thing as medial axis. I think this one's a simpler and faster function, if I remember correct, but it works in a slightly different way. ST skeleton, for example, does connect to the containing polygon. At all of the places that there's a node in the containing polygon, it will create a line that connects to those nodes. So we end up with extra lines that have to be removed instead of needing to create new lines. But once we've taken out those false intersections, then we can go through the PGR node network, create topology, and then do our routing. And all of this code is available in the indoors SQL script that you can download. So a couple snippets from that process. The first step, as I mentioned, was cutting out these overlapping polygons. And I want to be very transparent that this fix right here is very specific to the exact data that I'm working with here. I was looking for a corridor with rooms inside of it. It was a very contained example. To really scale this to large scale routing setup, you have to be a little bit more advanced than what I did here. But here we're using we're unioning the rooms that are inside the corridors and inside of the ST difference function. And then here I use ST multi because the table that I'm ultimately saving this data in defines it as a multi-geometry instead of a singular geometry. So the inverse of the previous where I was collapsing using line merge. So again, the exact scenario is going to drive exactly what you need to do. Your source data tables and the sources that you're working with are going to heavily influence the actual SQL code you need to write. And then to create here's where I found the false intersections that ST straight skeleton creates. And it might look a little complicated at first. The from and the join are finding the intersections between the generated axis and the polygons that contain them. The left join is a pretty common pattern in SQL when you're looking for missing data, where it exists in these tables, but not over here. We're using a left join And then we add the where is null in the clause to find those that are missing. And the join to the indoor point table is finding where there's doors. So this step prevents us from pretending like we're ghosts and walking through walls. We're not. We need to open the door and go through that way. So this is removing those false intersections. And just a final look at that route through there. From the back of classroom 314 to the back of the classroom 303, we're looking at just over 90 meters to walk around that. And considering there wasn't a single line string in the source that I used, I'm really pleased with the ability to do this type of routing through this kind of area. Just a quick reminder that if you're using both of these functions, a little here, a little there, be aware that there are differences. One of them connects to the polygons and the other doesn't, and they both require an additional step afterward. One of them you have to add more lines, one you have to take out lines, and it really going to depend on the scenario that you're working with, which one you probably want to choose. So access controls are a major challenge when it comes to working with routing, because there is so much nuance in all of this. These are 4 keys: access, traffic, barrier, waterway, dam, with 4 values. Each one of these keys has other values that can influence access and ability and speed and legality of the travel. So to boil it down to a single scenario, if it's access private, can it be routed? Well, it's going to depend entirely on your scenario. If it's private, but it's an emergency route for an ambulance, can they travel through a private drive? Probably. If it's my private drive, I can drive there, but maybe you can't unless I've invited you. So, it really comes down to conditional logic depending on this scenario. The same approaches that I've used for the previous challenges are the same approaches I use for this type of scenario. You have to find intersections, you have to identify what should or shouldn't be, and then we modify the edge network is how I typically would access this, and either set a cost to a negative to prevent routing, or increase a cost to discourage routing. I do that with pedestrian networks. Pedestrian network, I can walk on a residential street, but I'd prefer to walk on a sidewalk if it's available. So if we crank up the cost on the residential street relative to the more appropriate pedestrian route, you get a more appropriate route for a pedestrian. It doesn't mean that it won't completely exclude a residential route. If it saves you from walking around an entire subdivision, it might be a good idea to just take that shortcut. So a few techniques that I try to follow when I'm doing routing, and this is really just data and data science and data management 101 for a lot of purposes. You need to understand your data. Document everything you possibly can, especially the edge cases, especially the things that don't work right. So when unexpected results come through, you have kind of a cheat sheet of, oh yeah, we intentionally didn't handle levels for this one, so we got a false route because we're intentionally not trying to manage that issue in this case. Clean your data before you start working. As you're working through it, clean it some more, keep cleaning it, identify it, and throughout the whole process, document what you're doing. And of course, test and iterate. And it's going to be, if you start with the expectation that you're going to iterate and repeat and retry, it's less frustrating when you have to do the repeat and retry, because I have yet to have a routing project from start to finish in one take. That's just not realistic. So to finish with, just a little shameless plug. Last month, I released an ebook called Mastering PostGIS and OpenStreetMap. There is a free section preview in there and a blog post that kind of talks about it. 4 of the chapters in this book are related to routing directly. It all uses OpenStreetMap and talks about data quality and cleaning. I'm biased. I think it's great. So thank you.
Thank you very much, Ryan. That was a beautiful little run through routing.
Thank you.
So it sounds like a lot of problems in the like non-traditional network world do come down to having like a good skeletonizer, a good dimensional reducer. And I don't know what your take is on the ones we have, but my take is they're really terrible.
They are a means to an end.
Yeah.
Yeah, I'm not going to criticize the quality of them. I don't think I have any experience really to actually criticize the nuances of them. These two different tools, the straight skeleton and the medial axis, they both work differently. And the medial axis doesn't work for pedestrian routing. You get just really strange zigzags that, okay, maybe it's the I'm walking home from Boulder Bars at 2 a.m. route.
Yeah.
But they serve different purposes, and they're ultimately a workaround. A medial axis through a lake, I mean, if you just go straight through the lake, you're completely ignoring the dam in this case. And so, and then, we need to get into some applied calculus in order to do the math to figure out inflow and outflow rates. And, so it's just using a line, it gives us a place to go. And so, that solves a huge problem from my perspective. So that's why I'm not going to criticize the nuance of the implementation, because I think even if the skeleton was a little bit better for in whatever way you're envisioning, it doesn't solve the larger problem of water dynamics.
Right.
So.
Yeah. I come to it from the point of view of someone who saw some very nice algorithms for this 20 years ago. In fact, one of the projects which drove PostGIS development was a watershed project, which was built around doing some work like this, turning planimetric data into a routable network. And we had a nice little router. It was in Java, or a nice little skeletonizer. It was in Java and did a wonderful job. And you fed it a polygon, and you also fed it the input points. And it just did a beautiful job. Well,
that would be nice to be able to feed it the input points. That would be because then it takes away that, because either way I go, there's post cleanup. So if I could just add that as an input, because I can know that we know that at the input, we have that input. So that would save a post processing cleanup step, which would be nice.
Yeah. So, and yeah, eventually we got that algorithm working sufficiently that it could skeletonize like 2 million different lakes in BC, everything from Williston Lake to the pond next door. So it was pretty good stuff. So I feel like, I really should figure out how to do that in GIS, recover that knowledge.
I'll test it when it's ready.
Yeah. Do we have any other questions? Don't think so. So okay, we'll move on along. Thank you so much for an amazing talk.